So we now have the Lorentz transformation equations in hand. That's good. That's exciting. Let me give you a couple of notes, a couple of observations, extensions of these ideas that are worthwhile to keep in the back of your mind before we head onwards. So, observation number one. I have only spoken about x and t and x prime and t prime. Poor y and z haven't had any role in anything that we have discussed. And the reason for that is we've been looking at motion just in one dimension, so y and z basically just come along for the ride. And that means that if I write out the Lorentz transformation equation, including y and z, and y prime and z prime, the additional two equations are pretty simple. Y prime equals y, and z prime equals z. There's no change in the y dimension from team train to team platform. Similarly, z prime and z. So if we were to extend, that is, team train and team platform, to have a y and a z, and a y prime and z prime, they would just come along for the ride. Okay, note number two. I've pretty much already made use of this in the derivation, but what you call team train, what you call team platform, is a matter of perspective, in that team train can claim to be at rest with team platform moving, or vice versa. And that means that the equations we derived must have a simple incarnation from the other reference frame's perspective. And indeed, we already have indicated what that is. So if the relationship between t prime and x prime and t and x has a minus sign where the v is concerned, it's going to be a plus sign if you go to the other frame of reference, because from their view, the other frame is moving in the opposite direction. That's the only change. So to go from t and x to t prime and x prime, that is the equation that you use. Again, y prime and z prime just coming along for the ride if we're just moving in one dimension. Another point that's worth emphasizing is that you can make the Lorentz transformation equation look a little more symmetric if, instead of framing it in terms of t and x, you use c times t and x, right? So the speed of light, we choose these clever units where it's equal to 1. That can obscure the symmetry that's inherent in these equations, because ct has the units of a length. It's a velocity c times a time. That's a length. And so if you frame the Lorentz transformation in terms of ct, that's a length, and x, which is also a length, there's a chance that the equation looks more symmetric between them, and indeed it does. So just throwing in factors of c in a way that keeps the equations the same. Notice now that ct and x are playing exactly the same role. They're just interchanged from one equation to the other. If you like to think about transformations using matrices, which are the way that we can describe linear transformations, you can do that as well with the Lorentz transformation. So sometimes you'll see the Lorentz transformation in this form, where we look at a column vector which has ct, x, y, and z. And given that, the transformation between the two has this nice, simple matrix form. Final point is this. I showed you some fun animations early on where we had clocks at every grid point in a three-dimensional space. And we had three-dimensional grids of clocks moving through other three-dimensional grids. But then I said, those pictures may be nice, but we're not going to work with the full three-dimensional examples most of the time because it's a little complicated. And as you see, we've only focused on these one-dimensional examples over here, but yet it's really rich, right? We've been able to come to these surprising conclusions about space and time. Having said that, it's nice to at least see once in your life what the Lorentz transformation looks like if you do allow motion in a full three-dimensional space and you take account of x, y, and z for both the stationary and the moving frames. Here is what the Lorentz transformation looks like in that case. So to make the formula a little bit easier to read, we introduce this notation beta. So beta x, beta y, and beta z, the ratio of vx to c, vy to c, and vz to c. And in terms of that motion, if that is the motion of the moving frame, then the relationship between c t prime, x prime, y prime, z prime, and ct, x, y, and z takes this form. Now do you understand why we didn't do the three-dimensional case? It's a pretty complicated looking formula. You can derive it. It's not actually that hard to derive. We don't typically make use of this in many of the calculations because it becomes unwieldy, but nevertheless, it's good to see that you can do it, and this is the way in which the space and time coordinates in the moving frame relate to those in the stationary frame if the two frames are moving with that velocity, vx, vy, and vz. Now, that is a complicated formula to actually deal with analytically, but of course, you can program a machine to do the work for you. And in this demonstration that you'll play with on your own, the full three-dimensional Lorentz transformation is taken into account. So we imagine in this demo that we have a torus, a donut, if you will, and we're going to ask ourselves, what will the donut look like from the stationary frame if it is moving with a velocity that now can be through the full three-dimensional space? So you get to pick the direction that this guy is going to be moving by moving this around in this space. And you can pick the magnitude of it, not just its direction. And by moving this around, you can see that the donut can take on a variety of interesting shapes based upon the motion that the frame of reference that it is stationary in, the frame of reference that is moving relative to us, that is, causes the object to have a distorted look. So it's fun to play around with this. It's using the equation that we have up there on the board. It's a little bit involved to work out by hand, but there you have it. That's the impact of the full three-dimensional Lorentz transformation.